the examples today and the stuff that you guys just did, we're going to use all the vocab. So you guys can make notes of what it means or go in and fill it in later or whatever you think is going to be useful to you. Or even just you can even just use the vocab words to point things out on the examples or stuff like that if that helps you, okay? Sometimes having like just definitions from the book and stuff is not that helpful. So just depends on what you use as a learner. So we're going to talk about monomial, degree of a monomial, polynomial, degree of a polynomial function, how to write it in standard form, turning points, and end behavior. Okay, so we're going to try and use those things as we go through the stuff that we're looking at. So when you guys sketched these functions, okay, so these were all polynomials except for the first one. If we wrote it as an expression, if it wasn't an equation, so if the f of x equal was gone and we just wrote 2, that would be a monomial, okay? So what's the difference between a monomial and a polynomial? Not necessarily a variable. That one could still say 2x and still be a monomial. Okay? Good. So this one only has one term, where the other expressions that we've set equal to f of x have multiple terms, okay? So the first one, if it was just an expression, if it didn't say f of x equals, would be a monomial. This second one would be a binomial. This third one would be a trinomial. And then after trinomial, we just call them polynomial. So this one's still a trinomial, but the Quintic function listed here is just a polynomial. Okay? The Quintic function is a trinomial. Okay? So I've just named things based on how many terms they have in them. How many things are being added or subtracted together when it's simplified. Okay? So the degree of a monomial is just the power on the variable in that. So notice that the constant function has degree 0, right? So it has one term, and the term is 2. Does 2 even have a variable? No. So if you wrote that expression with an x in it, it would have to say like 2x to the 0 power, because x isn't really there, right? So that makes its degree 0. Now, if we look at, say, the Quintic function right here, it has 3 terms in it. Each term has its own degree. The 4x has degree of 1. The 5x cubed has degree of 3. And the x to the 5th has degree of 5. The degree of the entire polynomial is 5. Okay? In the Quintic function, the degree of this entire polynomial is 4. How do we pick out the degree of an entire polynomial when it has more than one term in it? What am I picking out when I've labeled this one degree 3, this one degree 4, this one degree 5? Catherine? Good, the biggest exponent. So if it's just one term, it's the exponent on x. But when you start adding a bunch of those together and you make a polynomial that's no longer just a single monomial, you just pick the highest power of x, okay? So degree is based on the highest power of x. We talked about naming the function by how many terms they are, but then look how these functions were labeled. This wasn't labeled a trinomial, it was labeled a Quintic function. So there's 2 ways to name something. One way is by how many terms it has in it. Monomial, binomial, trinomial, after that just polynomial, okay? The other way to name something is based on how big its degree is. So degree 0, meaning no x's show up, then the function is called constant function. Degree 1, meaning the highest power of x is to the first power, those are lines. They are linear functions. Highest power is degree 2. Those are quadratic functions. So you've experienced all of those before, okay? And so you're a little bit more familiar with those names. So these names will be new. We won't go higher than degree 5 as far as something that we have to know the name of, like, immediately. If it's degree 3, we call it a cubic. If it's degree 4, we call it a quartic. If it's degree 5, we call it a quintic. Okay? I'm sure the ones after that have names, but they're not used as often, and you don't have to know the names, okay? So basically, these functions can be named 2 ways. This one can be called a Quintic trinomial. This one could be called a Quartic polynomial. Okay. This one could be called a cubic trinomial. This could be called a linear binomial. that okay with everybody? As far as number of terms is the nomial part of it, okay? And then the degree is giving you another name of the function. The quartic, I called it a quartic polynomial. So anything above 3, we just go with polynomial. It doesn't get a more specific name. That's it, okay? All right, are we okay with like kind of the nomenclature, as you would call it, all the naming system that's happening here? All right, so why this is important is that the degree of function can tell us something about the functions. You guys have experienced this before. When you don't see x, when you have a constant, what do you guys expect to show up? Alex is showing me, right? Horizontal lines, right? We know how to graph those. All of a sudden, when there is an x in it, meaning there's a slope of some sort, what happens to the line? It has like some sort of because of the slope. We've graphed quadratics. What do those look like? They get to turn all the way around, right? And so all of a sudden, instead of their ends going different directions, they come back and go the same direction. Okay? So now you guys have gone and graphed and one example of a cubic, one example of a quartic, and one example of a quintic function. Okay? What was the general shape of your cubic function? Jenna?
It was kind of like a snake. It went like up and then down and back up.
Okay, good. So went up and down and back up. So I'm going to cheat. Don't look at me. Okay. And so it looks something like, I'm not drawing it in the right place. All right, what about our quartic function? What did it kind of look like? Alex? Okay, so it could be like a W, right? Did this one turn out like a W when you guys graphed it? No, but it can look like a W. We'll talk about this in a minute. Anela? It's like, this one looks like a funky looking parabola. And that, it depends totally on what's like in here, okay? So this one kind of went like, it looked like it was going to be a parabola, but then it had like this weird non-symmetrical part of it on the other side somehow. But it can look like a W. We'll talk about that in a minute. Okay, what did our quintic function look like? Okay, so it looked like the cubic one with like an extra turn in it, like this or something? Like that? Is that okay with everybody? Okay. So, and then you know what your constant looks like, you know what your linear function looks like, and you know what your quadratic function looks like. So what do you think the degree of the function has to do with the shape of the function? What are the patterns that we can find based on degree and shape? Any patterns that you guys see? Which ones seem to be similar, different, stuff like this? Sen? Okay, so the highest power is the maximum amount. It has something to do with the maximum amount of turns that it can make, right? So our linear function that has degree 1, how many times does it turn around? Never, right? 0. Our quadratic function, which has degree 2, how many times does it turn around? Once. Our cubic function has degree 3. In this picture, it turns around twice, okay? These are called our turning points. That was one of your vocabulary words. That's like a straightforward one, right? Like turning point, point where it turns around, okay? Now, this is a quartic. It did not turn around a bunch of times, right? Okay? This is kind of the proof that you can turn around a certain number of times, but you don't have to, okay? But then your quintic turned around 1, 2, 3, 4 times. What do you think is the relationship between the degree of the function and the number of times that it could turn around, the maximum number of times it can turn around? So again, degree 1, 0 turning points, not allowed to turn around at all. Degree 2, 1 turning point. Degree 3 could have up to 2 turning points. Degree 4, I don't know, okay? Degree 5 could have up to 4 turning points. Jenna? Good, so write that down. So the number of turning points is at maximum. So it doesn't have to be 1 less than the degree. Okay? So this is our example of it doesn't have to be, right? The quartic, you guys know how Alex said it's a W, okay? He might have typed did you type something in wrong or do you just know more than us, Alex? Oh, you didn't put in the 7x. So he took out the 7x, so he still put in a quartic, right? And his, instead of looking like this, looked like this-ish, okay? So it could turn around 3 times, but does it have to? No. So the maximum number of turning points you can have is 1 less than the degree, okay? So that's important, because that also contributes to some other things, right? What's the maximum amount of zeros or solutions or x-intercepts that a line can have? 1. What's the maximum amount of zeros or x-intercepts that a quadratic can have? 2. What's the maximum amount of x-intercepts that a cubic can have? 3, because it can turn around twice, so can it cross through, it can cross back through, and then it can cross through again. Does it have to have 3? No. What if we scooted this whole thing down? It would have like 1, right? Okay. So this quartic would have like 2 solutions. What if Alex's quartic had the x-axis running right through here? 4, okay? And our quintic in our picture has 5 solutions. Could it have another solution? Only if it's allowed to turn around again, but based on the pattern we saw, would it ever turn around again? Not unless we change the degree higher. So what's the relationship? So number of turning points is 1 less than the degree is the maximum amount of times we can turn around. We don't have to, but we will. How is the degree related to the number of solutions? Anil? Good. Okay. The maximum number of times you can cross the x-axis equals the degree. Does it have to? No, but the maximum amount of times. Now, some of these do have to cross the x-axis at least once, and some of them don't, okay? So make that note as well. I don't have lots of space for notes, sorry. Okay. So the maximum number of x-intercepts equals the degree. All right. What else seems to be a pattern when we look at these pictures and relate them to the degree of the function? Like if I wanted you guys now to graph something that was of degree 6, you guys would know the most amount of time across the x-axis is 6. What about what the sketch would kind of look like? So I can see it in my head. If it does cross it 6 times, a lot of turning arounds, right? But what about like the ends of the graph? Ram?
If both ends go in the same direction, if it's odd, they go in opposite directions.
Good. Do you guys see that up here? So with odd powers, our ends, one goes up and one goes down. So one's going towards infinity as far as the vertical stuff is concerned, and one's going towards negative infinity. Infinity and negative infinity. Infinity and negative infinity. Whereas when the degree is even, either both are going towards infinity, or we know a quadratic could get turned around the other way. They could go towards negative infinity. What makes it flip around and go the other way? Think about your quadratics. What would change it from both ends going up towards infinity to make both ends go down towards negative infinity? The a value, right? If it had a leading thing that was negative, it would flip it over. So that's true for all of our functions. So these odd degree functions, and we have to be really careful because later you're going to learn about even and odd functions. You're going to want to confuse it with what we're talking about now, like when you go to pre-calc honors, okay? We're not talking about the function is even or odd in general. We're specifically talking about degree. So if the degree is odd, one end goes up towards infinity, one end goes down towards negative infinity. If you put a negative in front of this, what it would cause is those ends to do that in the different direction. Okay, so an easy kind of way to remember is to think lines, right? Positive lines, the left goes down towards negative infinity, and the right goes up towards positive infinity. And then if all of a sudden you made the lines slope negative, the left infinity and the right would go down towards negative. It's true for every odd thing, that the left goes down and the right relationship changes. Okay? Is this all right with everybody? So degree can tell you a lot. So in this unit, we are going to graph cubes like we graphed quadratics with transformations and all that stuff. The transformation stuff is not going away. So if you did not learn it last unit, you need to invest in learning it. But the rest of these we're just going to learn to sketch like we did here. We just want some main characteristics of them to be true, but then we're just kind of filling in the shape without exact points. Okay? People don't spend a lot of time graphing all these polynomials that are like super crazy and stuff like that. Okay? All right, so our examples. Let's do one at a time. Okay, so the first example is just about naming. And again, you guys can just write the example. You can write the problem and just like go through. You don't have to copy all of this stuff, okay? And if you just want to take some other notes, if you don't have the note guide, but you're a person who normally does, know that you can get that. Like the video's on there. You could scroll through and get the answers at different times if you didn't get something, okay? So a polynomial in standard form means like a quadratic in standard form. Ax squared plus bx plus c. Highest powered term down to lowest powered term. So this one would be rearranged to be negative 6x cubed plus 3x squared plus 5x minus 4. That's it in standard form. If there were like terms, I'd combine them together. Yes?
I thought it was negative with the
Oh, sorry. I know. I don't know what to do with that. Here, we can go like this. Let's stay in there. I don't know what it will. I didn't tie this on. There we go. Okay, so name the polynomial based on the degree. So remember, there's two ways to name our polynomial. One is based on the degree of the function. One is based on the number of terms. What is the name of this polynomial based on its degree? Zen? Okay, so good. She gave us both. All right, so the degree, no, you're okay. The degree is 3. So its degree name is cubic, and it has 1, 2, 3, 4 terms. Anything more than 3 is just referred to as the generic polynomial. A binomial is a polynomial too. It just has a more specific name because we use them often. But as they get larger and larger, they're not as common. We don't give them all these specific names. Plus, it'd be hard to keep track of at a certain point, right? Is it okay for naming for everybody? Okay, not too crazy in the naming department. So then all the other thing that we want to do at this point is look at graphs and kind of determine a couple of things about them. And some of the things we look at are going to parallel what we've done before with graphs, and some things are going to be a little bit different. Okay? So I'm going to scroll this up here. That way we can look at everything and just look at those graphs. Okay. So the first question up there says determine whether the degree of the function is even or odd. How many real zeros does each polynomial function have? And we're just doing this by looking at the graph, not the equation, okay? So look at the graph in part A. Do you think the degree should be even or odd of that function? Anila? Even. So why does she think even? Somebody else. Fill me in. So Alex is going like this, okay? Jenna? Good. The ends have the same kind of behavior. They're both either going towards positive infinity or towards negative infinity. That lets me know that it has even degree, right? So this function would be of even degree. And according to the graph, how many real zeros does it look like this function has? How many times, what's another word for zeros? X-intercepts. How many times does it hit the x-axis for real on the graph? 3. Oh, I guess we could debate about whether that last one, let's say the last one touches, okay? So 3, okay? So we'll say 3 real zeros. All right. By raising your hand, somebody that hasn't spoken to us yet, tell me what you expect the degree of the function that's shown in picture B to be. Liam? Even. Good. I expect the degree to be even. Now, I can't really say for sure what the degree is, but what's the smallest degree that that function could be, given how many times it like turns around and stuff? It has to at least be a quartic, right? Because it turns around 3 times. So it at least has to be of degree 4. Could it be of degree 6? It could. I don't really know without looking at the function. Because remember, the number of turning points is kind of the maximum it can have. Doesn't necessarily mean it does that. Okay? Somebody else, number of real zeros for this graph. Good. Real zeros. All right, the graph in part C. Somebody new, raise your hand. Tell me what type of degree you expect the function to have. Good. Do you guys see the behavior different at the end? Okay. So we would expect this function to have odd degree. What about the number of real zeros? Clear? Good. So 2 real zeros. So this part right here, estimating the turning points, you're literally doing what your calculator does to find minimums and maximums. So if we had put this into the calculator, it can still find minimums and maximums even if they're not the absolute minimum. This is the absolute minimum of this function, right? Is the lowest point it goes. This is a minimum. They call it a relative minimum because it's not like the absolute thing, but in that area, like relative to what's around it, it's like a minimum, right? So that's what they call it. So when we're talking about turning points, it's all the minimums and maximums in their little area, so all the relative minimums and maximums, and we would just estimate them. If they're showing us a graph, if we had the equation to put into the calculator, we'd use the calculator's minimum maximum function to calculate that. So we're just going to do this one because I think that you guys can pick points off of a graph, okay? So like this point right here looks like maybe -2¼ is the x-coordinate for it. And then the y looks like 1, 2, 3, 4.5 maybe. That's one turning point, but this graph has 3 turning points, right? So I'd list that one. I'd also have to list that one up there that looks like maybe an x of 1.5 and a y of 2.5. And then that third one right there that if we're saying it's hitting, let's say we see it hitting at 3, looks like the 0.30. Does everybody understand that listing turning points is just listing those relative minimums and maximums? And that if we're doing it by hand, we just do this. We make the best list that we can based on the graph. Otherwise, the calculator can give us more definitive values. Okay? Is it okay if we don't do the other ones and just pick out those turning points? Okay. I think we can do that. All right. Intervals of increasing and decreasing. Okay, so remember what we talked about before. When we list intervals of where the graph is increasing and decreasing, what are we listing? X values or Y values? X values, right? Parts of the domain. Even though we're looking at when it goes up and when it goes down as we're going across, we're not listing how far it goes up and how far it goes down. We're trying to tell them in this piece of the graph, this domain, it's going up as you go left to right. And then in this piece, it's going down as you go left to right. Okay? So the graph starts out here. As we go from left to right, the first piece of the graph is decreasing. Okay? Let's assume there are arrows on the ends of these. Sorry that there are not. So we'll assume that it begins decreasing. And so that would be from -infinity until it hits a turning point, right? So with parabolas and with absolute value functions, we did this. And the vertex point was important because it kind of split up the two intervals, right? On one side, it was increasing, and on one side, it was decreasing. The same thing is true here. You just, instead of having like 2 things that happen, you have like this splits it up between this and this, but then this splits it up again, and there's another piece, and then this splits it up again, and there's another piece. So it's decreasing from -infinity till here, and I said that this point seems to occur at an x value of -2.25. And I'm going to label my interval, sorry. So this was decreasing, right? All right, then it hits that turning point, and then what's happening? So we were decreasing till here. Now as we can continue to go across the graph, we are increasing until the next turning point, right? So our first section of increasing interval then goes from -2.25 until that turning point, which I said has an x value of 1.5. But I'm not done, right? Because there's more stuff. So I'm here. Now that I hit that turning point, as I continue to go, I am now decreasing in this little section right here from Sorry, you guys. That should say 0.5, yes? Yeah? Do you guys see what I'm talking about? I'm going to go through and make a correction right now. Okay? So just so you guys see, I was saying 1.5 because I was thinking it was over there. But do you guys see that that turning point is lined up with an x value of 0.5? So that should have been the case right here. And right here. Is everybody clear with what I just changed? Okay. You guys can correct me too, because I know you guys sit out there and you know mistakes I'm making. All right, so we did the first decreasing interval, the next increasing, and then at that turning point it decreases for a little while again. So when we add a second portion onto the decreasing interval, we like to say it's the union between two different things, like it's this one and this one too. And so we just put this U right here in interval notation when you want to list more intervals. Like instead of like a comma in English when you're making like a list of a bunch of things that fall into the category, the U tells people you include this interval and the next one that I list. And if you need another one, then the next one, etc. Okay? So this now goes from 0.5 to 3 as that next decreasing interval. And then there's another increasing interval again, right? So because there's a second increasing interval, I want to unify one and another, okay? And my second increasing interval is from this turning point here and for the rest of the graph. So it's from 3 to infinity. So is everybody understanding that decreasing and increasing we're visually finding the same way we did before? However, now it's not like one part of it can be increasing and one part could be decreasing. There could be many of each or one of each and many of another or something like that, just depending on how many turning points there are. Yes? Sorry, say that again. Uh-huh. No, it just intervals. So like here's one interval, here's another interval. Yeah, as long as between them, that's fine. It wouldn't even matter the order that you list the intervals in. Like you could list this interval and this one. But remember in intervals, you cannot switch these two because it's supposed to be smallest to biggest when you list your intervals. Does everybody understand here these aren't points? Okay. Does everybody understand that you could have where the numerical values are? Used brackets if you wanted. Because remember, for our turning points, there's kind of an indefinite idea of whether they're part of that interval or not, okay? But not with infinity because it's not an exact value. Is this okay for increasing, decreasing intervals? Are we good with not going through the other two examples of those two? We're okay with this? Because there's one other thing we're going to add to the list that you guys have not done before. And this is end behavior, okay? So I'm actually going to scroll it back down and rate on the graphs for end behavior. Is everybody okay if the writing goes away here? We have what we need. Okay. All right, so we have not done end behavior before, but it's something that we are going to talk about. So it's just basically how the graph is behaving at the ends. You know how you guys were saying like, oh, they go in the same direction. They go in different directions. This side goes up, this side goes down. They both go up, they both go down. That's the idea, but that's not like the right way to say the idea mathematically, okay? And just be aware that if you look in your book, it's not going to use the same notation that we do. It says like up, up. That's really nice, but where your guys' pathway, that's not enough, okay? We're going to write end behavior like you would write it in calculus and stuff like that so you guys get used to the notation. So on the left side of this function, the function is going up towards infinity. So the left end of the function, it goes towards infinity. And on the right end of this function, it goes towards infinity, okay? The right way to say it is like this. There's two ways that you guys can write this. First of all, you need to make two statements every time because you need to tell me what's happening on the left and you need to tell me what's happening on the right. So end behavior is a thing that's written in two sentences or two mathematical statements, okay? One way is to say as x goes towards. So we don't say left and right mathematically. If I want to say the left, what is x going towards when you go towards the left of the graph? The x values are going towards negative infinity. So I'm basically just saying on the left side of the graph, but I say it like that. And then I want to say if it's going up or down, but that's about y values. So I say f of x is going towards what? If it's going up, the y's are going towards infinity. If it's going down, the y's are going towards negative infinity. So this is saying as x goes to negative infinity, or as I go to the left of the graph, so infinity. Okay, so that sentence describes what's happening on the left. And now I need to describe what's happening on the right. So the difference in the sentence would be, the beginning would now say as x goes to infinity, okay, because I'm going towards the right on the graph. F of x goes towards, is the right side going up or down? Up. So infinity. Okay, so it will always have everything here exactly the same. The only thing that's going to change based on your graph would be these over here, because those are the things that you're always changing. But you're always going to say on the left side, the y's are doing this. On the right side, the y's are doing this. So it's just whether they're going up or down right here that's going to change. Okay. The other way to say this, I don't know if you guys will like this or not, is written with a limit, like what limit does the graph approach kind of thing. And underneath the limit, it has little notation about the left or the right, like x going towards negative infinity means the left of f of x. So when you write something like this, you're saying the limit as the function goes way to the left. So like what happens to your function as it goes to the left? Does it just start becoming 0? Does it start becoming 1? Or does it shoot way up towards infinity and go down towards negative infinity? And so we said it goes up towards infinity. Okay? And then you'd have to make another statement like that about the right side. You guys can use either of these notations. And no matter which one you use, okay, the beginning will always be the same because you always have to say on the left side of my function, here is what's happening. On the right side of my function, here is what's happening. And the only thing that's going to change every time are those parts of that statement. But you definitely need two statements, no matter which way you write it, to describe end behavior. Okay? Is this okay for end behavior? Yeah, Jenna. Uh-huh. Yep, it's just like, in your book, like I said, is like really, it just lists like up, up, up. So like this graph would have the same end behavior. Part B would have the same end behavior as part A, because it doesn't matter what's happening in between. It's just talking about the ends of the graph. Part C here would be going down on the left, but going up on the right. So if I knew I had to do end behavior, like from a student perspective, and let's say I liked this method, the minute somebody asked me about end behavior, I would know I have to write this much. Like one statement about what's happening to the function on the left side, one statement about what's happening to the function on the right side. Then I would look at the left side and say, is it going up or down? Down, which means towards negative infinity. On the right side, does the function go up or down as I move to the right? Up, right? Then infinity. Okay? So again, this first part is all the same, or with these statements too, this part that is changing at the end, because you're just trying to say what's happening on each side. So you need to get used to the notation, but then really have on your head, like, this just means what's happening on the left side. This just means what's happening on the right side. Is it going down or is it going up? Okay? All right. So your homework, you guys can look on Canvas, is skill 1 and 2. They're not